All right, thanks Kaveh for this nice introduction and listing like a bunch of stuff I did. So yes, as Kaveh already said, I'm working on a lot of CPU security and side channel stuff, and together with my team and during my PhD, I discovered a lot of things, and you've probably read my name somewhere on some of the papers in combination of some of all these vulnerabilities also Kaveh mentioned. And when I started doing that was like 10 years ago, I started with traditional side channel attacks, like this textbook thing we started. And this was like indirect measurements, doing some timing measurements, observing timing, and getting metadata about some secrets, right? So you learn something about the secret. You don't directly get the secret. And that was already like super fascinating. It's like, wow, I'm measuring some timing differences here, and then in some way I can infer some crypto key from that. And I was like, that was amazing. And nowadays it was like, yeah, well, that's kind of lame. And soon after that, we discovered transient execution attacks. And this was kind of like the holy grail back then. You actually leak direct data. You really get the secrets out, you leak the data, you read the crypto keys, you don't have to infer them from some timing measurements, some access patterns, you directly get the data. Still, there was indirection involved, so this was still related a lot to side channels, right? You still had your covert channel part to use some flush and reload to decode the data that you leaked. But this was already something super interesting, and nobody would have expected when I started. And now we're moving more and more into architectural vulnerabilities, where nobody really had expected that in the beginning, where we really directly read data from our victims. So Kaveh already mentioned, for example, Epic Leak. You just read from a memory address, you get the secrets, and that's it. And that's super bad, because it's very easy to exploit, and this is not good for security. But this is something we've seen in the last couple years, and we get more and more of these things. And transient execution attacks in the middle, like Meltdown, I consider them one of the key enablers. So they bridged this gap between traditional side channels and then architectural vulnerabilities where we directly read the data by combining them in a very nice kind of wormhole, putting them together. But this was not only the key enabler for all these vulnerabilities that we see now in the research on them. Another key enabler that I often like to mention was Intel SGX. And Intel SGX was a very, very nice trusted execution environment. Came out in 2015, 2016. We were able to buy that. We were excited to get a machine with like, yes, it has Intel SGX. We finally can do some research on trusted execution environments. And why was that a key enabler for a lot of the things? Because it changed our threat models, right? So before all of that, and when I started, all the threat models for side channel attacks were about unprivileged attackers, which can just run some code in user space and then try to attack something. And now suddenly with TEEs and with Intel SGX, one of the TEEs that you can just buy and use, and it was easy to use, there was an open source SDK, it even worked on Linux, so really great, not our Windows only SDK. We could now do attacks and research where the attackers are privileged. And that opened an entire world of new types of attacks, right? So there was a lot of stuff that was being published, and I also see like Yo here doing a lot of these things, working on TEEs, with control channel attacks, attacks with performance counters, with segmentation, with undervolting, looking at branch predictors in a more precise way. These were all things that were only possible by running privileged code and using these features that were only meant to be used by an operating system, but not for like traditional attackers. And I also always consider SGX as like one of the stepping stone in research, because this really enabled some of the attacks and only led us to some of the attacks that would not have been possible without that. So for example, mentioning Yo here again, with the discovery of Foreshadow, he did that on Intel SGX. And that was, of course, on a TEE. But it then later turns out like you can also do that from in a virtual machine, and Herbert just had a nice paper about that, doing that with foreshadow NG, also working from a VM. But nobody would have probably discovered that without the research on TEs. Similar things, the research on predictors, which helped a lot with Spectre attacks, LVI, Epic Leak, and other types of attacks that were only possible with having such a TE. Unfortunately, SGX fell into a bit of a disgrace because it was beaten so much by academics. It's still architecturally a nice design, right? But it was designed before all these microarchitectural attacks, so they were, of course, out of scope. But, well, media also doesn't really care a lot, and academia doesn't care a lot. So this was kind of destroyed, and now nobody really wants to touch it anymore for security purposes. And that was kind of sad to see for Intel, being beaten by all these attacks. And there was another vendor for x86, AMD, and in 2019 they were quite confident that they can do much better, right? So they had this statement in 2019, AMD believes that our hardware paging architecture and protection checks help AMD processors not be affected by many side channel vulnerabilities, regardless of whether simultaneous multithreading, SNP, is enabled or disabled. And this is a bold statement. And back then, sure, we've seen a lot of research on Intel CPUs, not so much on AMD, and was also, well, kind of true, because there was not so much on AMD, it was mostly on Intel's. But threat models shift, so things have to be re-evaluated, and they constantly shift. And they shifted already with SGX, going from unprivileged attacks to privileged attacks. And they shifted again, also for AMD, with confidential VMs. So a kind of new generation of TEs, where now you don't have like this SGX enclaves, where you have to split your application into a trusted and untrusted part, and the trusted part runs in a protected way, which is kind of inconvenient for application developers, but there was a much more clever idea to just put everything in a virtual machine, have this virtual machine encrypted, protected, and that made it way more easy. So this was also nicely explained at Usenix Security 2016 by David Kaplan. I think he's also here somewhere, yes. So very clever idea. And the first version of that was SEV, Secure Encrypted Virtualization, with secure, kind of not the secure that we actually consider secure for security, but also looking at your talk back then, you said we protect against a benign but vulnerable hypervisor. We're not protecting against a fully malicious hypervisor at this point in time. We consider a hypervisor that is generally well-intentioned but may have bugs. So in SEV, this was mostly encrypting the memory and nothing else. And this was then also shown by academics, like, yeah, well, this does not protect against any of these attacks. So the second iteration, SEV-ES, then also added some encrypted state here, the ES, to actually also protect not only memory, but also register state, which was, well, kind of some overlook maybe, to also make sure the register set in a context switch is protected. But this was not enough. Academics are kind of creative in breaking things. So every vendor has seen that. There are a bunch of people here, and I guess a large fraction here is trying to break stuff. Maybe quick show of hands, who likes to break stuff? Who likes to build and defend stuff? Okay, well, it's nicely distributed. So also for SEV-ES, there were kind of a lot of attacks against that, also looking at things that were not considered or not implemented in the SEV designs, like starting in 2018, with you could remap pages to then extract plain text because the order of the pages was not relevant. You could attack the thing by downgrading the firmware to a vulnerable firmware version. You could still get a valid attestation by reordering parts of the memory, or you could inject things into guests because there was no integrity protection. It was about confidentiality. And this was also a statement from AMD, saying like SEV and SEV-ES features are not designed to protect guest VM memory integrity. It was about confidentiality, and integrity was more seen as a bonus. But nowadays we also know integrity is necessary. So without integrity, we cannot get confidentiality. So from this, next iteration, third time's the charm, right? SEV-SNP, secure nested paging. So this is now the state-of-the-art variant of SEV. And there we have now finally a statement where AMD says SEV-SNP is designed to prevent software-based integrity attacks and reduce risk associated with compromised memory integrity. The basic principle of SEV-SNP integrity is that if a VM is able to read a private encrypted page of memory, it must always read the value it last wrote. That makes a lot of sense, right? You write something, you read it back, it should be the same value. If that's not the case, then your integrity is gone. So now we say, okay, now it's really SEV is protects against attacks, and it's for confidentiality and integrity. And this is kind of when we also in our groups are like, okay, this is now a cool design. Now let's see if it breaks. And getting creative again is like, okay, is there something maybe AMD has overlooked when doing that? And we looked at something that the older people know who have worked longer with x86, legacy instructions. x86 is great, right? It's so old, it has so many instructions and so many instructions that most people don't even know that they exist. And they still exist and they still work and they have to work because it's like the main selling point of x86, running code that is old. So you can still get your newest machine and run your DOS operating system and it will somehow work because everything is still supported. And one of these instructions that was really interesting, some of them are just like, yeah, okay, they exist, but one of them I really liked was the invalidate instruction. And the invalidate instruction is one of these old cache maintenance instruction that flushes the internal CPU cache. And the interesting detail there is it does not write modifications back to memory. So it just gets rid of the cache content. And if you have some modifications that are just in the cache, not written back yet to memory, well, they're lost. And this is something that was considered by Intel. So in the Intel manual, it has like an explicit warning saying use this instruction with care. Data cached internally and not written back to main memory will be lost. Software should instead use the write back invalidate instruction because there's, well, not really a reason to actually use that instruction nowadays, especially not when you have a fully booted multi-core system running a 64-bit mode. Running an invalidate there, I mean, we tried that at the beginning, like naive experiments, you run an invalidate, everything dies. Of course, there's so much modification in the cache, and if you just get rid of that, everything is corrupted. But that didn't stop us. So it's always, if you see a crash, also looking at Kave, right, you should further investigate that, because it could be interesting. And we have, why do we have Ray? Ray? Ah, yes, here. My PhD student, Ray, he was like, okay, I need to further look at that, and I need to build something out of that, an attack. And that's when he did the CacheWarp attack. And the CacheWarp attack from a high-level perspective looks like that. You have the hypervisor, which can be malicious in the SEV threat model. You have a victim VM. And then, of course, you have your hardware, like your CPU with the cache and the DRAM. And your victim VM does something like reading memory first, printing something. So what happens, you read that from DRAM. It's transparently put in the cache. So you have a copy in the cache. Then you output that, and it's fine. Then your victim VM will modify this data. This modification only happens in the cache first. There's no direct write back. That will happen at some point if the cache has like a victor line or something like that. So it's only in the cache. At that point, the attacker interrupts the victim, runs the invalidate, so it removes all cache content. So this modification is gone. Switches back to the victim VM. The victim reads that data. It's not in the cache anymore. Cache is empty. So it has to be fetched from DRAM again, and the attacker gets, the victim gets the old value and outputs the old stale value. All right, So this looks like a functional problem at first. You're working with stale values. And that's not directly a security problem, but it destroys integrity because that really violates the statement we had before, like if you write something, read it back, it should be the same. So we have an integrity violation here. And this was like then also a statement like, wow, that's not great, but it's also not terrible, right? Because integrity attacks by themselves do not directly compromise a VM. There was a statement there that you need software inside the VM that utilizes the incorrect data, and then you might be able to compromise that also. So this was kind of the take on that. I was like, okay, but is it really that complicated to go from this, like we use stale values to actually compromise a VM? And again, I had my students who are, some of them really creative CTF players, play around with that and coming up with nice tricks. And one of the simplest attacks that they did, which is so easy, it fits on a slide, and I always like if attacks fit on a slide, is exploiting the pseudo binary. And what does the pseudo binary do in a, well, kind of simplified code here? It has a variable that stores your current user ID. Then it asks the operating system, like, what is actually the user ID? If this user ID is 0, which is, well, coincidentally the one for root, then it will just continue as root because sudo is already root. Otherwise, it will like ask for your password. All right, and we can already see here, variables are 0 initialized. We get the value, the real user ID from the operating system. It's a write to this variable, and then there's a read. So if we call the invalidate here from the hypervisor, this write never happens. And our code simplifies to, we have a variable that's 0 initialized. If it's 0 initialized, we continue as root. Very nice, very easy, and we're instantly root. And of course, you can consider like, okay, this also fits the official statement. You need special software to actually pull that off, because like by accident it works that way. People said like, oh, that's a stupid software bug. Who would initialize a variable to 0? Just initialize it with something else, and it's not going to work anymore. But well, it's just a symptom. I mean, as software people know that initializing to 0 makes a lot of sense. And this was like our targeted attack, showing that this is easy to do. But there's way more. There are way more writes that do not depend on specific software implementations. So of course we have like these explicit writes here. We have a lot of compiler introduced writes. So if you look at your disassembly, you see a lot of operations where things are moved to the stack, from the stack back to registers, and so on, that we don't see on a source level. And then one very interesting thing, return addresses. If you think about function calls, if you call a function, well, then the return address is pushed onto the stack. That means there's a write. There's a write of the return address to the memory. And we can revert writes, so we can drop this write. So we can drop the saving of a return address. And now some of the software exploitation people will already be like, yeah, that's not good. If we can modify return addresses, that's probably bad. But we can't directly modify them. We can just like not have them. So how do we exploit that? And this was also a very clever idea. That's a bit of a brain fuck here. So I tried to illustrate that with, unfortunately, some assembly here, right? So we go into the details. This is an attack primitive we call time warp, where we essentially jump back in time in the control flow. Okay, how does it work? So we have two functions here. This return 0 function that just moves 0 into RAX, like the register containing the return value. We have function read1, just moves the 1 into RAX, so essentially it's a return 1 in C. These two functions, and then the main body, what does it do? They call read1, so we call this function. RAX should get 1, then we compare, is RAX 0? Of course it's not. If so, we jump to the win function, so we will never end up there, normally. And then we call the return 0 function to set our return value to 0, the RAX to 0, and then we jump to fail. So we expect to go to fail. So what can we do now with CacheWarp to actually get into win? if we call into return 1, we get RAX set to 1. On the stack, we have the saved return address. Where will it return to? To here, the second line here, so main 2. And we go back, we do this comparison. Of course, RAX is 1, this is not 0, so the jump equal does not trigger. We continue, we call the return 0. So we go into this function. On the stack, now we have the saved return address. Where we want to return to is then line 5 here. That's after the call. In this function, we set RAX to 0 then. But we first invalidate this store. So we don't actually save the return address. And we go back to the old stale return address, which was here from the previous call. But now we set register RAX to 0. RAX is 0. If we return, we use the old return location, and we go back in the control flow, go back there after the first call. And now we are at this comparison. RAX is 0. We compare that to 0, and now it's true. We went back in the control flow, but still have the new data, and then we can jump to our win function. Yes. So this is on like the toy functions, already complex, but exploiting that in real-world programs is a nightmare. So we still had that. So we had students working on that for hours and days, finding things where they could actually do that. And they did that, for example, in OpenSSH to jump back in the password comparison, so to compare the password hash not with the entered password hash, but with the stored password hash, so comparing things with itself, which was always true, allowing attackers to log in into SSH without knowing the password. So this is on a high level. I left out a lot of the details. Like, of course, you have to synchronize that, right? You really need to trigger the invalidator at the correct position. So you need to actually step to the store, and this also, as said before, key enabler SGX. You did a great job with SGX step there in introducing ways of getting to one instruction with interrupts, and then we had SEV step later on. We also built our own framework. But these ideas originate from there, and how to go somewhere. Then you step before the store. Then you flush the entire cache, so everything else that was modified is committed to memory. Then you step over this one store, let the victim do this store, and then you call the invalidate and throw away the store. So it's actually not that complicated with all the building blocks we already had in the community. So really we had generic exploits. They really are possible, and it's nearly independent of running software, because also of how x86 works, and where we have a lot of implicit stores, and when we can revert them, we really can do a lot of harm in a very, very generic way with this type of attack. So this was really a very interesting type of attack. And from first it looked like, okay, you have like a functional issue, you have stale data, to like, you can exploit specific applications, to like, yeah, this is relatively generic here. So of course this had to be mitigated as well. And this was mitigated not really in the way I like mitigations, but super effective. So essentially the mitigation for that was getting rid of that instruction by unconditionally forwarding it to write back invalidate. So, well, you can't use that instruction anymore, which is not a big issue, right? Because nobody needs that, but it's still removing features as a mitigation is not my favorite way of mitigating things. I was like, okay, this was with a microcode update, so that can be applied, and everything is safe again. And of course, this is what we ultimately also want, also in my research group. Of course, we like breaking things, because it's like kind of the thrill of breaking things, but in the end, we want to make the world more secure. So, of course, disclose that we work together with vendors, and we want to make sure we have mitigations that are deployed. So when we make that public, when I talk about these kind of things, you cannot exploit them anymore. So then also, this issue has not been found to impact AMD's 4th generation EPYC processors like the Zen 4 microarchitecture and Zen 5. So this was then fixed in hardware, which is the much nicer fix, but of course, way more complicated to do. And you could say like, okay, this is now the end. Now we have a good architectural design. There was this oversight with legacy instructions. We couldn't see any other legacy instructions. I'm pretty sure also at AMD, they looked like at all the other instructions that could interact in a bad way with SEV. And if there was something we overlooked, they probably caught it and also fixed that in Zen 4 and Zen 5. But don't underestimate my PhD Ray here, who's also in the job market. He was like, well, a nice CPU got there with Zen 4, Zen 5. Be a shame if anything happened to that, right? Let me dig deeper into stuff and see if I might still be able to break that, because he has a lot of time and he likes to break stuff. So that's what he did then for, well, his main focus for the thing after CacheWarp. And he managed to do it. So he came up with another attack called StackWarp that was just released like 3 weeks ago, January 16, when the embargo ended, and now we hopefully have all the CPUs out there fixed, so nobody can exploit that in the real world. So what is StackWarp in a nutshell? Again, SEV-SNP, now Zen 1 to Zen 5, so everything. And essentially with the StackWarp attack, you can, from a malicious hypervisor, manipulate the stack pointer inside a confidential VM. So you can move it up and down however you like. And again, here, like people playing CTF, it's like, okay, if I have control over the stack pointer, then that's really bad. So this is like, in a nutshell, what can be done. The question is like, how and why do you find that, and what's the reason for that? And it started out with, at some point, some discussion about chicken bits, right? So who knows chicken bits? Yeah, okay, a lot. So these are like these bits that you can configure in your CPU to turn certain features off. As already mentioned, like hardware is a bit more difficult to update than software, and sometimes you might not be 100% confident in a feature you implement in hardware. So you can also add a chicken bit, and then at boot or the operating system can like disable a feature, and then it's not available anymore. And we've seen that for plenty of features. Intel also used that quite a bit, like for TSX, they disabled these kind of things when it turns out that they can be used for attacks or when they were simply not working the way intended. So we're like, okay, we want to look for these chicken bits that can turn features on or off. And these are mostly not documented, except if they are needed to actually disable a feature. And so we were looking for them and trying to find them. They're typically model-specific registers and seeing what happens. And our goal was to like have such a chicken bit that we can flip, such that the virtual machine keeps running. Because if it just dies, that's kind of boring. That's an availability issue, and it's not the biggest issue. It should somehow corrupt the architectural state. So something should be broken. And best case, triggerable in parallel when the victim is running, and we can do something as the attacker. Now the idea was essentially going for like not normally turning on or off, because this is boring, because these chicken bits should work, right? Because they are meant to disable or enable a feature. So we kind of went for a Schrödinger's chicken bit by cycling it on and off all the time, so that even we don't know if it's on or off this feature at the moment. So only when this feature is kind of used by someone, this victim will realize if this feature is dead or alive, and then something might or might not happen. So it's kind of exploiting race conditions in chicken bits and seeing what happens. And we had some observable effects. So one of these MSR, which was already known for chicken bits, is this documented MSR here, that already had some bits to disable certain features that turned out to be not working well, like for some errata here, something with prefetching, with CL flush, and other bits were not documented. But we suspect that like many of them will be some form of chicken bits that disable some functionality. And one of the bits that we flipped was bit 19. And with bit 19 flipping that, we kind of got weird effects in a virtual machine. We got stack traces like that with illegal instructions and like huge stack traces. Like, I don't know, debugging is hard, right? But nowadays we have anyway AI, so we put that into ChatGPT, and I was like, what is going wrong here? And ChatGPT was actually very helpful. It's like strongly indicates control flow got redirected with a misaligned jump return. Look here, you likely have a smashed stack overwritten return address. I was like, oh, that's kind of interesting. So we get memory corruption with stack modification by flipping a bit in a hyperthread. That should not happen. That should definitely not happen. But what does happen? Of course, these LLMs are not good at doing the research that we do. Even though they are marketed as PhD level, they are far from that. So we actually had to do our own analysis. So we also looked at performance counters, saying like, okay, what happens when we change that bit and we execute instructions, and we see like, oh, this bit somehow affects stack operations. So everything that's like an implicit stack operation, like pushing, popping from the stack, calling, returning, suddenly requires more micro operations to be executed, and explicit updates to stack pointer, fewer micro ops, and everything else is unchanged. So that pointed at something. That's the stack engine. So we knew about this thing, that it exists, but we never really spent much thought on what it actually does. It's a very nice optimization. There's also a very nice paper I can recommend from Kave's group. He did that just a few months before we had our paper, also looking at the stack engine, also on AMD, and also how to disable and enable it. So the stack engine essentially is this optimization where instead of updating your stack pointer every time you do like a push or a pop, what you do is the CPU keeps the delta to the real stack pointer. So the real stack pointer register is never updated, but only an internal offset is updated, and then the CPU works like with this internal stack pointer of real stack pointer plus the stored offset in the stack engine. And that's pretty nice, then you can break dependencies and you don't have to execute like additions and subtractions on the stack pointer. And of course, you would have a wrong stack pointer register, so if someone tries to read that, right, like getting the stack pointer value into a register, you have to synchronize that. So then you really take the offset from the stack engine, apply it to the real stack pointer, reset the delta to 0, and then you have them in sync again. So this is kind of the stack engine optimization, very simplified in a nutshell. And this MSR is there to enable and disable the stack engine. So if the stack engine might not work as expected, you can disable that. But like you do that once and not all the time. And this is exactly what CacheWarp does, like enabling, disabling the stack engine at a point where you're not supposed to do that. So here we have like an attacker, we have a victim, we have the stack engine. Here illustrated the victim stack, and the attacker now changes the offset inside the stack engine by doing a stack operation. So with this offset stored inside the stack engine, then the attacker disables the stack engine, which kind of freezes the offset inside the stack engine because it's not used anymore. Then the victim is running. When the victim is running now without a stack engine, it just directly updates the stack pointer. So a push like updates the real stack pointer, writes to the stack. Now the attacker can turn on the stack engine, quickly switch back to the victim VM, and then this has to be synchronized here. And this offset that was stored from before, that was created by the attacker, is now applied inside the victim VM to the victim stack pointer, and the victim stack pointer moves. So the attacker did a pop before, so now this pop effect happens in the victim VM, and the next operation in the stack, like the second push on the victim VM, works now with a corrupted stack pointer and overwrites the previous one because the stack pointer was adjusted. You can replace that pop with a push here, then you move the stack pointer in the other direction. You can do multiple of them, so you can shift the stack pointer up and down however you want inside the victim VM. That breaks, of course, again, integrity. You need to be be a bit creative again to exploit that. But after some brainstorming and a lot of time investment, students also came up with a bunch of attacks, so fault attacks on crypto, something that's sometimes quite easy if you only need to corrupt some internal states somehow. You can quickly do that. So that works. Again, doing the sudo exploit, that also works. And kernel code execution, because if you can move the stack pointer, well, then you can also kind of choose what the return addresses will be. And if you do that in the kernel space, it's pretty nice. You can essentially get a ROP chain in there via a network backend and then do CacheWarp to set the stack pointer correctly, and then you execute code with kernel privileges. So again, this very simple modification of like a stack pointer offset is sufficient to break all these things. So this is something that I really admire about humans, that they always find reliable exploits. Some of them are so dedicated in showing that stuff is broken and breaking stuff. They are so motivated by that that they can take the smallest corruptions and build full privilege escalations out of that. Something I've already seen like 10 years ago with Rowhammer, like 1 bit flip, and then everything breaks. So this is something very important to consider. If it's like the slightest corruption, you can find a way to make that into a reliable exploit. So what we've seen here is essentially Pandora's box of CPU vulnerabilities that has just been opened, I would say, with the transient execution attacks, where suddenly it became clear that it's not only about side channels, but we can really get to data. And we can break confidentiality, we can break integrity. LVI was like first kind of breaking integrity in some way in a transient domain. And now we see that on an architectural domain as well. So security vulnerabilities in CPUs are real. It's not unexpected now that we see it, because, well, it's also just kind of software that's written. And side channels were always helpful, and I guess will still be helpful in the future to see these things and also at some point to discover them, because you just see some indirect effects often. It's not like software that just crashes, gives you a stack trace. CPUs don't do that. And side channels are thus often necessary to actually see the things where things break. I guess we will see more of these architectural bugs. It's also not surprising, because like we had a lot of bugs. Just looking at the public error test, there are multiple thousand bugs documented in AMD and Intel CPUs, but most of them like functional problems. But looking at this entire creativity here in this room, I'm pretty sure we can also revisit some of these just functional problems and make them into security problems. And I wouldn't be surprised if that is going to happen more and more now that we also have this idea that these things can happen. I would still say vendors were kind of lucky so far, relatively. We haven't seen large-scale exploitation yet, at least not that I'm aware of. Please correct me if I'm wrong. I'm always looking for like real-world incidents, and just like few things popping up here and there, but no idea if these things really happen. And also from the threat model, it's also still fine. So all of the vulnerabilities you just saw, they work in the cloud, but from a malicious hypervisor. If you have a malicious hypervisor, we anyway have big problems. Should be fine with confidential VMs, but the most pressing issues would be the ones that are exploitable from within a different virtual machine. If you could do these things from a co-located VM, this would be really, really bad. And luckily, we haven't seen too many of these things that are exploitable from inside VMs. And also, we have seen, luckily, that we have software mitigation. So also, thanks to people here who like to build stuff and defend stuff, coming up with clever ideas how to make sure it cannot be exploited on a large scale. And also, with microcode, a lot of creativity went into that in making sure nothing can be exploited by applying some workarounds there. Still, my expectation is I haven't seen any exploits so far, so my exploitometer is like it's still at low. Do I expect exploits in a few years? Maybe, yes. If we get first rid of all the other low-hanging fruit, like software vulnerabilities, misconfigurations, and stuff like that. Could be. If someone really builds automated tooling, like have a metasploit for microarchitectural attacks, yes, I definitely see it. So I've seen first tries of doing that with like Spectre attacks. If we get an easy tooling where we just like enter the IP address and then it runs some microarchitectural cool exploits there, yes, I guess we will see that in the wild as well. So it's good if you make sure things are secure, and if you first break them academically, fix them, involve the vendors, make sure we have good designs so that this is not going to happen. So takeaway, looking at a lot of the things we did, it's a checklist for not doing these things, so don't use this checklist, please. As like adding shared state, it's like, yeah, maybe reduce shared state. Sharing is not caring in this aspect here. Having undocumented behavior, we know it's security by obscurity. We don't do that. Focus purely on confidentiality. Sounds nice at the beginning, but it's very easy to overlook that also breaking integrity then can break confidentiality. And having cross-thread interactions, hyperthreading, simultaneous, multithreading, whatever you call it, yeah, keep them as isolated as possible if you really have to keep them. So I personally like it, but for security, it's a nightmare. So if you look at these things, confidential VMs are very fragile systems. So it's really, really difficult to get them perfectly secure. It's not a magic box where you can just put your crappy software in and then it's fine. So know what they can protect against and what they can't. Always think about integrity, and that breaks completely differently. And it's probably more harder to get right than confidentiality. It's more than just adding crypto. And also from a microarchitectural perspective, we love these optimizations, right? Because we want faster CPUs, we want to have longer battery runtime on our laptops. But they also often violate assumptions. So it's important, and I've seen that multiple times, that if you're working with engineers that focus on performance, also have some people focusing on security and like telling them a bit like, no, maybe not that fast here. And we don't really want to die like that here. So this is really a difficult trade-off to do, but I think we're getting better and better at that, and CPUs getting more and more secure. And I hope at some point we will have confidential virtual VMs in a way that we can't break them anymore. That would be very nice for the security of everything. That brings me to the end. So thanks for your attention. And we might still have time for questions. Thanks. No? Is it on?
All right. While Yo figures it out, thanks a lot, Michael, for the engaging and very clear keynote. I really liked it.
Thanks.
So maybe I will be selfish and ask the first question.
Go ahead.
So there are a lot of like young people in the audience, and I think so these attacks, they're very cool. But I feel like sometimes it's very difficult to get started if you haven't done that in the past. So what advice do you have for somebody who's just starting in this field and want to one day build an attack like what you described, one of the attacks that you described?
Yes, this is a very good point, and I had that discussion already. Also looking back, I explained that in one of my last talks. 10 years ago, when I started, these things were easy, right? Also looking at them from now, you were super happy when you just did some histogram, you had some cache attack, some simple one. And nowadays, things get more and more complex, so it's actually not easy to get into that anymore. We have a kind of, luckily, this advantage that we already have established research groups doing that. So joining them already helps. They can provide a lot of expertise and get you slowly into that. And I also always tell my students, like, start simple. You're not going to start like day one, my first microarchitectural attack. I'm breaking confidential virtual machines. I'm breaking something like that. This is not going to happen. You still need the basics. And the basics are still involved in all of these things. So just like building your first flush and reload, doing some cache eviction, that sounds like super lame nowadays, but is essential to actually get like the tool set for doing that. And then these things look scarier than they are. So yes, VMs are way more scary than just like processes. But when you know like your tooling and you've played around with these things, you have to play a lot. Maybe you have to play more nowadays than like 10 years ago. But getting into that works. So also I see that with my students. They start with the basics, also some already in my lectures with a bachelor thesis like that. When they look back, they say like, okay, well, I was really stupid back then. It took me like 2 months to implement a flush and reload on AST tables. But it's like, yeah, but that's expected. And 10 years ago, that was great. You could have written a paper about that, a top tier paper. Nowadays, it's like, yeah, everybody knows how to do that. But this is where you have to start. So maybe we just have like a bit more startup period. But I think we'll also shorten that, at least some institutions, by having nowadays lectures about that kind of thing, right? So we learn earlier. So for me, it was like at the end of my master's, beginning of my PhD, the first time I heard about these things. Nowadays, I have students in their bachelors learning about this, doing these things, so we have to move that a bit earlier. And that also helps because then they can already start like in their master's PhDs with a nice set of skills.
As a follow-up, perhaps I'll shout, it's fine. That's for the recording. Oh, it's for the recording. Okay. For the recording.
Maybe he doesn't want to be recorded.
I don't want to be recorded. I just want to hear from you, sort of as a follow-up on the previous question. Would you advocate writing Metasploit for microarchitectural attacks?
Oh, that's a very good question. No, I don't want to see it.
It would lower the bar for entry, right?
It will happen. I think it will have an impact in industry because then really a lot more companies would care about these things, I guess. I don't want to have that. I don't want to like see everyone running around exploiting stuff. I don't like that. I want to have a cloud that's secure that I can use. I also wouldn't want to invest the time in doing that. But I guess we will see it at some point. So there was already, I don't know if you've seen that, there was this Spectre in the Wild discovery. That was kind of a module for such a closed source black market Metasploit equivalent, but it had a Spectre module that allowed to just provide a file name, and it then had different Spectre gadgets hard-coded there for different kernel versions. It chose the one for the correct kernel and then read a file. So yes, we see professional groups already using that. They were also using prefetch side channels for breaking KSLR first and things like that. So I think this is already happening. We're just not aware of that. At least I'm not aware. Maybe you have better contacts into black markets.
I like the implications there. But if it's already happening, why shouldn't we, embrace it and make it and democratize it? Basically, make it available to legitimate researchers also.
Well, asking the question back, what do you expect from that? What do you want to gain from that?
I think a lot more attention from the industry to actually fixing this, and actually more engagement from academia and other researchers.
Yes, maybe yes.
Other questions for our keynote speaker, please?
I think this person got up first.
Thanks, Michael. To keep going on this talk, like if we don't have this Metasploit framework that democratizes this sort of attack. Like, would it be likely that state nation actors will be doing this and we won't hear about it because these attacks are stealthy? Or
I'm pretty sure. So I'm pretty sure this will happen, and this might already be happening. So looking back at history, right? Nation-state actors, they have smart people and they figure things out before we do in academia, and they keep that secret and they will never tell you. So it's not unlikely that these things happen, yes. But also I think, I mean, maybe it's a good idea, I don't know. I'm not advocating for building these kind of things. Maybe it's a good idea, but I also think that in the past years, vendors showed way more interest in that. So I still remember the time when we disclosed Spectre Meltdown to some vendors. That was difficult, and they had a hard time understanding what we actually wanted. So we had this one call where we said okay, you have this vulnerability in your CPU, and the question was like, who are you? What do you want? Do you want money? Are you blackmailing us? And it's like, no. We just want to tell you that you have a vulnerability. And like, yeah, but why do you do that? I mean, what's your incentive? And like, we're just academics. We just figured it out, and we want to make sure your CPUs are also secure. It's like, okay, they didn't really wrap their head around that. That was in like 2017. Now we're in 2026, and a lot has changed, right? All the CPU vendors have security teams. They handle these things well with embargoes, with working together. Well, some better than others, but still all of them do. And they all understand that. And I think most of the CPU vendors have their dedicated microarchitecture security teams now internally looking at these things. So I think the awareness is there for CPU vendors, also for cloud providers. I know that they really care about these things. So maybe we don't have the awareness in the general public, but I'm not sure there's so much benefit.
Hi, I would like to move from the Metasploit, and my question is about the fix. I think I've seen in the paper that it was fixed by microcode update. And have you tried to reverse it, and how the AMD has fixed that?
So for the CacheWarp, yes, that was a kind of what we've seen, simple fix. So there's like this one bit in a model-specific register where you can change the behavior from the invalidate to make it appear as write back, invalidate, and back, and they just block the access to this bit. So you cannot make it invalidate. It's always write back, invalidate. For StackWarp, Ray, they also blocked the access to that. I don't know. For StackWarp, I'm not sure, but I think this also affects like just changing that bit.
So in runtime, you cannot set the register, the chicken bit?
I guess so, but for StackWarp, I actually haven't looked at that. We also wanted to reverse engineer that, the patches for Zen 5, because there's this nice Google project with the entry sign to look at microcode and decrypt that from AMD. But unfortunately, their public version does not support Zen 5, so we could not decrypt the microcode. Would be interesting to see what is actually done there. That was actually, we actually wanted to implement the fix ourselves because, well, with this entry sign tooling, you can write microcode yourself, but not for Zen 5.
We have time for one last quick question, and then we have to go get some coffee.
Right, thanks for the talk. I don't want to keep this too long, but this is a relatively new space of research as far as I can see. And as you mentioned, there was this Pandora box where it was opened and then everyone was exploring it. But now that I feel that I have this feeling that we're closing in on everything that's in the whole CPU design and everything. Is it what do you think? Is it a feeling that's at the back of my hand and I should make it shut up? Or are we really just, have we explored pretty much every single thing that's already in the current implementation, and is the research eventually going to stagnate because of lack of things to explore overall?
That's a good question. I had that thought myself also multiple times, like, can we go forward with that the next 5, 10, 15, 20 years until at some point I can retire? It's hard to predict the future, right? But I think there's still so much to do, so all of these things are pretty much low-hanging fruit. There are so many things inside CPUs that we haven't explored, that we don't even know exist, that we don't understand. I had these discussions with unnamed CPU vendor where we said like that, and this was like, yeah, your explanations, they're good enough, but the reality is much more complex. And also when talking about these things, like, and then there's this element and this element and this element inside a CPU, where you always see like on like chips and cheese or on wiki chip, these nice diagrams. It's like, this is a very simplified way of how CPUs work, and internally they're way more complex than that. So we'll also find more stuff, and also CPUs are not like done. It's not like, okay, we have CPUs now. They are like that. They change all the time. They get more features, more complexity. So we have more ways of exploring things. So I don't think we're at the end. People also said similar things for memory corruption, right? Like 30 years ago. Like, yeah, we are done now. We know how to solve that. Did we get rid of them? Not really.
That's great, because we're only the 2nd edition and we want to have a future. So
exactly.
So thanks a lot, Michael, for an excellent keynote. There was a lot of debate. I'm sure we can continue that over coffee.